Good morning everyone. In previous class we discussed about the under reinforced section, over reinforced section and valence section. So here we discuss about the determine the moment of resistance for the section shown in figure. So here we define the moment of resistance, and how can we find out the moment of resistance by using the force in compression zone and also in compression tension zone. So here FCK is provided 20 Newton per mm square, Fy is provided 415 Newton per mm square, and also a section is provided which is consist with 3 numbers of 12 mm dia bar, and the effective depth which is provided 310, and the breadth is provided 250, and d dash which is clear cover is provided 40, and the solution is first we write the given data, then we define the moment of resistance by using the compressive force or by using the tension force. So here FCK is provided 20 Newton per mm and Fy is 415 Newton per mm square, and breadth B is provided 250, effective depth D is 310 mm, effective cover 40 mm, or we can write here clear cover, and force of compression first we calculate. So force and compression is 0.36 into FCK into B into X. So here the 0.36 into 20, FCK value is 20 and B value is 250, and the total value of force of compression is 1800 into X Newton. Same we compare the steel section. So here the area of tension steel ST or AT we find out by multiplying the 3 into pi by 4 into diameter square. Here the diameter provided is 12 mm dia, so 3 into 113 mm square. So force of tension is 0.87 Fy into ST. So 0.87 into Fy, that is value is 415, and ST value is 3 into 113, which is the area of one steel bar in tension zone. The total force is 122,400 Newton. Then we going through the force of tension and compare the force of compression. Then we get the value of X. In case of force of tension, no unknown is there, and in case of force of compression, here one unknown is there, which is X. So by comparing those two forces, one is tension force, another one compression force, then we get the value of X, which is the depth of neutral axis. So here force of tension that is equal to 122,400 Newton, and force of compression that is equal to 1800 or 1800 X. So here X is equal to 122,400 by 1800, that is equal to X is equal to 68 mm. Then the XM we find out by XM here the maximum or limiting depth of neutral axis we can find out from the IS 456. Page number 72. By using the Fy value, normally the X max is normally depend upon the Fy value or grade of concrete value. So here the grade of concrete is grade of steel value. The grade of steel is provided for 415, 500, and also we use with a mild steel bar which is 250 mm. And here 415 for 415 grade the XM is 0.48 into D, and for the 500 grade the XM is 0.460. Normally these two are used in the calculation process. So here two value is normally provided in this table. And here it's depending upon the depth of the section. So depth provided 310, so XM is equal to 0.4 into 8 into 310, because the grade of steel also provided 415. Okay, so for 415 the XM is equal to 0.48 D, so 0.48 into 310, that is equal to 148.8 mm. Then the XM is greater than X, So therefore the depth of neutral axis is equal to 68 mm and limiting depth of neutral axis, that is equal to 148.8 mm. Then we are going through the lever arm, which is Z. We consider the D minus 0.42x. So D we given in the question 310 minus 0.42 into x, which is 68. We consider as the neutral axis, which we can define from the equating two equation of tension force and compression force equation. So here the value is 310 minus 0.42 into 68 is equal to 281 mm. So x, here x less than x max or x limit, then it is the under-reinforced section. Since this is an under-reinforced section, moment of resistance is governed by steel, and moment of resistance with respect to steel is equal to tension force into lever arm, which is Z. Okay, so mu is equal to 0.87 into Fy into St into Z. Fy value is given 415 and St value is given 3 into 113 and Z value is, we can find out, 281. So the mu is equal to 0.87 into 415 into 3 into 113 into 281, that is equal to 34.40 kilonewton into meter. So here we define the mu moment of resistance value by using these values of FCK, Fy and D, or which is the effective depth, and B, which is the breadth of the section, and the most important, by using xm and x, we define the value of moment of resistance here. Then we discuss about the design of a section. So in case of design of a section, here how can we design a section? We discuss. So here one question is given. Design a rectangular beam to resist a bending moment equal to 45 kilonewton meter using M15 mix and mild steel. So here one solution is given. The beam will be designed so that under the applied moment both material reach their maximum stresses. Normally beam we design to reach the maximum stresses. So assume ratio of overall depth or breadth of the beam equal to 2. Breadth of the beam is V and overall depth, which is denoted as capital D. Therefore, D by B is equal to 2. For a balanced section, factor bending moment, which is equal to moment of resistance with respect to concrete, moment of resistance with respect to steel, and the load factor into bending moment we can calculate, or which is, suppose we consider the example, the bending moment is given 45 kilonewton meter. So we can find out the factor bending moment by multiplying the 1.5 value. So 1.5 into 45, that is equal to 67.5 kilonewton into meter. So here we find out the moment of resistance or bending moment. So the today time is over. The remaining part we discuss in the next class. Thank you.